Hello there, and welcome to Before Law, where we take our time with the big questions and let wonder breathe without rushing toward easy answers. Tonight, we're not going to talk about distant galaxies or black holes or the edge of the observable universe. Instead, we're going to look at something much closer to home, something you can feel beneath your feet right now, and ask a question that might make you see it in an entirely different light. What if Earth isn't the success story we think it is? What if this blue marble we call home, with its perfect distance from the sun and its protective atmosphere and its teeming oceans, isn't the rare gem in a hostile universe, but just the latest in a long line of attempts? What if, scattered across the cosmos, there are countless worlds that tried to do exactly what Earth has done and simply couldn't hold on? Before we dive deeper, I'd love to know where you're listening from tonight and what you can see from your window right now. Are you looking out at city lights painting the darkness, or maybe fields stretching toward a horizon you can barely make out? Perhaps you're somewhere where the stars are still visible, those distant points of light that might be warming worlds we'll never know existed. Take a moment to really consider where you are. The ground supporting you, the air filling your lungs, the gentle pull of gravity keeping everything in place. All of this exists on a thin shell of rock and water and gas, spinning through space at tremendous speed, held together by forces so precise that shifting any one of them by just a small amount could unravel everything we know. If this kind of deep, patient exploration appeals to you, if you enjoy taking time with ideas that don't offer quick solutions, I'd be grateful if you considered subscribing. It helps this quiet corner of the internet reach other curious minds who might want to sit with these questions alongside us. So settle in, let your thoughts slow to the pace of geological time, and join me as we consider the possibility that our world isn't unique in its beauty or its complexity, but in its survival. That somewhere out there, in the vast archives of space, lie the remains of planets that once held promise, that once supported life, that once looked as vibrant and stable as Earth does today, but couldn't quite make it to where we are now. The idea begins with a simple observation. When we look up at the night sky, we see points of light, but we rarely think about what might be orbiting around them. In the past few decades, we've discovered thousands of planets circling other stars, worlds of every size and temperature you could imagine, rocky planets closer to their suns than Mercury, gas giants larger than Jupiter, frozen worlds at the edges of their systems where sunlight barely reaches. But here's what strikes me as we catalogue these distant places. For every planet we find that might be capable of supporting life, we find dozens that clearly cannot. Too hot, too cold, too large, too small, atmospheres too thick or too thin, or made of gases that would kill anything we recognize as alive. The universe, it seems, is extraordinarily good at creating planets. It's much less successful at creating planets where life can take hold and flourish. This raises a question that astronomy textbooks don't often dwell on. If planet formation is so common, and if the ingredients for life exist throughout the galaxy, why don't we see obvious signs of life everywhere we look? Where are the signals, the artificial lights, the clear signatures of other civilizations that should be abundant if life naturally arises wherever conditions allow? One answer, the one we're exploring tonight, is that life does arise in many places, but staying alive, maintaining the delicate balance needed for complex ecosystems to develop and persist, that's where most worlds fail. They get started, perhaps they even flourish for a while, but then something changes. A climate shift, an asteroid impact, the slow evolution of their star, or simply the gradual breakdown of the very systems that once supported them. Think about our own neighborhood for a moment. Mars, our rusty neighbor, bears the scars of what appear to be ancient rivers and lake beds, minerals that could only have formed in the presence of liquid water. Evidence suggests that billions of years ago, Mars might have been warm and wet, perhaps even capable of supporting microbial life. Today it's a frozen desert with an atmosphere so thin you couldn't breathe it if you tried. Venus tells a different cautionary tale. Similar to Earth in size and composition, it may have once had oceans before a runaway greenhouse effect turned it into a hellscape where the surface temperature can melt lead. Both of these worlds might have been, for a time, what we would call habitable. Both lost that distinction long ago. And these are just our immediate neighbours, formed from the same cloud of dust and gas that gave birth to Earth. If 2 out of 3 potentially habitable worlds in our own system couldn't maintain their life-supporting conditions, what does that suggest about the countless planets orbiting other stars? The concept I want to introduce is what we might call the graveyard of worlds. Not a literal place, but a way of thinking about all the planets scattered throughout the galaxy that once held promise and now lie silent. Some never developed life at all, despite having the right basic conditions. Others might have supported thriving ecosystems for millions or even billions of years before crossing some threshold from which they couldn't return. This graveyard isn't visible to us directly. When we point our telescopes at distant star systems, we can measure the size and orbit of planets, sometimes even analyze their atmospheres, but we can't easily tell whether we're looking at a world that's currently alive or one that lost its life long ago. The difference might be subtle from such distances, detectable only through careful analysis of atmospheric chemistry or surface features that our current instruments can barely resolve. But the implications are profound. If the galaxy is indeed filled with worlds that almost made it, that came tantalizingly close to sustaining life over geological timescales, but ultimately fell short, then Earth's story becomes not one of inevitable success, but of remarkable persistence against difficult odds. Consider the sheer number of things that have to go right for a planet to remain habitable over billions of years. The star it orbits must remain stable, not too active in its youth, not evolving too quickly toward old age. The planet's orbit must stay within that narrow band where liquid water can exist on the surface, not drifting inward towards scorching heat or outward into permanent freeze. The planet needs a magnetic field to protect its atmosphere from being stripped away by stellar wind. It needs enough internal heat to drive geological processes that can regulate climate over long periods. It needs the right amount of water, not so much that it becomes a global ocean with no dry land, not so little that it becomes a desert world. The atmosphere must maintain the right composition, thick enough to hold heat and protect the surface from radiation, but not so thick that it traps heat in a runaway greenhouse effect. Large moons help stabilize the tilt of a planet's axis, preventing extreme climate swings. Giant planets in the outer system can act as gravitational shields, deflecting asteroids and comets that might otherwise cause extinction-level impacts. Each of these factors involves a delicate balance, and each can change over time. Stars gradually brighten as they age. Planets can lose their magnetic fields if their cores cool too quickly. Atmospheres can thicken or thin due to volcanic activity or the slow escape of gases into space. Orbits can shift due to gravitational interactions with other bodies in the system. For Earth, these balances have held, sometimes precariously, for over 4 billion years. We've survived massive asteroid impacts that created global winter conditions. We've endured ice ages that locked much of the planet in glaciers. We've weathered volcanic eruptions that pumped enormous amounts of ash and gas into the atmosphere. We've adapted to changes in atmospheric composition, including the rise of oxygen that was initially toxic to much of early life. But survival isn't guaranteed. Each of these challenges could have ended differently. A slightly larger asteroid, a more severe ice age, more intense volcanic activity, any of these could have pushed Earth past the point where complex life could recover. The fact that we're here to contemplate these possibilities is itself remarkable. Now, multiply this story by the hundreds of billions of stars in our galaxy, each potentially hosting multiple worlds. even if only a small fraction of planets start out with conditions suitable for life, and even if only some of those develop actual living ecosystems, the numbers suggest that millions or billions of worlds have at some point been alive in ways we might recognize. But how many of them are still alive today? How many manage to navigate all the hazards, maintain all the necessary balances, avoid all the potential catastrophes that could end their habitability? The mathematics of probability suggests that most haven't. That for every world like Earth that continues to host complex life, there are many more that tried and failed. This perspective doesn't diminish Earth's beauty or significance. If anything, it makes our world more precious. We're not just living on a planet that happens to be suitable for life. We're living on a planet that has actively maintained its suitability across enormous spans of time, through circumstances that have defeated countless others. The graveyard of worlds isn't a depressing concept, it's a humbling one. It reminds us that the conditions we take for granted, the air we breathe, the water we drink, the stable climate that allows forests to grow and seasons to cycle predictably, these aren't permanent fixtures of reality. They're temporary arrangements that require constant, unconscious maintenance by systems we're only beginning to understand. And understanding them becomes crucial when we realize that Earth's position in this story isn't fixed. We're not safely past all the dangers that claimed other worlds. We're still navigating them, still subject to the same forces of change that transformed Mars into a desert and Venus into an oven. The difference now is that we have something no other species in Earth's history has possessed: the ability to see these dangers coming and potentially do something about them. We can track asteroids, model climate change, monitor volcanic activity, even begin to think about how to deflect or mitigate some of the threats that ended other worlds' stories. But that ability comes with responsibility. If we're aware of the forces that could push Earth into the graveyard of worlds, and if we have tools that might help us avoid that fate, then our choices matter in ways they never have before. We're not just passengers on a planet that might or might not remain habitable. We're participants in determining whether it does. This brings us to a sobering realization about timing. The universe operates on scales that make human civilization seem like a brief flicker. Geological processes unfold over millions and billions of years. The evolution of stars spans even longer periods. Against these timescales, the entire history of human awareness, from our first glimpse of agriculture to our current technological civilization, represents less than a heartbeat. Yet within that heartbeat, we've managed to alter our planet's fundamental systems. We've changed the composition of the atmosphere, modified the chemistry of the oceans, triggered what many scientists now recognize as the sixth mass extinction in Earth's history. In geological terms, these changes are happening at lightning speed, faster than most natural systems can adapt or compensate. This acceleration matters because stability, the kind that allows worlds to remain habitable over deep time, typically requires slow, gradual adjustments. Earth's climate has remained relatively stable, not because it never changes, but because changes usually happen slowly enough for feedback mechanisms to kick in, for life to adapt, for new equilibria to establish themselves. When changes happen too quickly, these stabilizing mechanisms can break down. Feedback loops that once maintained balance can flip into runaway processes that amplify change instead of dampening it. We see hints of this in our planet's past. Periods when relatively small triggers led to dramatic, rapid shifts in climate or ocean chemistry that persisted for millions of years. The speed of current changes raises uncomfortable questions about whether we're pushing Earth toward one of these threshold moments. Not necessarily toward immediate catastrophe, but toward a state where the planet's ability to maintain the conditions we depend on becomes compromised, where the delicate balances that have kept us out of the graveyard begin to unravel. But let me pause here and acknowledge something important. When we talk about failed worlds and planetary graveyards, it's easy to slip into thinking that's depressing or hopeless, that we're doomed to join some cosmic collection of lifeless rocks drifting through space. That's not the spirit in which I want us to explore these ideas. The graveyard of worlds, if it exists, isn't a judgment on the value or beauty of those places. A world that supported life for 1 billion years before losing its habitability isn't a failure in any meaningful sense. It hosted countless generations of organisms, witnessed the rise and fall of ecosystems we can barely imagine, served as home to forms of life that may have been utterly unlike anything we know. Even a world that never developed life beyond microbes isn't empty of significance. The very fact that chemistry became complex enough to approach the threshold of biology represents an extraordinary achievement against the universe's tendency towards simplicity and decay. What the concept does offer us is perspective. It suggests that habitability isn't a given, that the conditions allowing complex life to emerge and persist are genuinely rare and genuinely fragile. This rarity makes every living world precious, not because life is the universe's intended outcome, but because it represents such an improbable and temporary victory against entropy. It also suggests that intelligence, consciousness, the ability to contemplate one's own existence and the nature of the cosmos might be even rarer still. If most worlds that develop life lose it before intelligence can emerge, then minds capable of asking these questions might be scattered very thinly across space and time. From this perspective, every moment of consciousness becomes remarkable. Every conversation about the nature of existence, every scientific discovery, every work of art or music or literature that captures some aspect of what it means to be aware in an apparently indifferent universe, these aren't just human achievements. They're achievements of matter that has somehow organized itself into forms capable of reflection and wonder. This brings us to one of the most profound implications of the graveyard hypothesis. If Earth is indeed surrounded by worlds that once lived but no longer do, then we might be among the very few places in the galaxy where the universe is currently capable of understanding itself. Where atoms forged in ancient stars have arranged themselves into patterns complex enough to contemplate their own origins, that possibility carries both privilege and responsibility. The privilege of existing during a time when our planet still supports not just life, but conscious life capable of recognizing its own rarity. The responsibility of making choices that honor that rarity, that don't carelessly squander what billions of years and countless unlikely events have made possible. When astronomers search for signs of life around other stars, they look for what are called biosignatures, chemical indicators in a planet's atmosphere that suggest biological processes. Oxygen paired with water vapor, methane that can't be explained by geological processes alone, seasonal variations that might indicate growing and dying vegetation. But there's another kind of signature they might eventually detect, one that would tell a different story. The chemical residue of a world that once had life but lost it. Atmospheres with the wrong ratios of gases, compositions that suggest a system falling out of balance. Surfaces that show evidence of past oceans or vegetation but are now barren. These death signatures would be much harder to recognize, partly because they might look similar to planets that simply never developed life at all. The absence of something is always harder to detect than its presence. But as our instruments become more sensitive, as we develop better ways to analyze the light from distant worlds, we might begin to distinguish between planets that never lived and planets that used to live. Finding such worlds would be both tragic and illuminating. Tragic because each one would represent the loss of entire ecosystems, billions of years of evolutionary history, perhaps even civilizations that never had the chance to spread beyond their home planets. But illuminating because they would teach us about the processes that end habitability, the warning signs that might help us recognize when a world is approaching its own limits. This is where the graveyard metaphor becomes more than just a thought experiment. It becomes a research program. By studying the worlds around us that appear to have lost their habitability, by modeling the processes that could end a planet's ability to support life. By understanding the thresholds beyond which recovery becomes impossible, we develop the knowledge needed to avoid the same fates. Mars offers us one kind of lesson about what happens when a planet loses its magnetic field and its atmosphere gradually bleeds away into space. Venus offers another about runaway greenhouse effects and the point beyond which increasing heat becomes self-reinforcing. The icy moons of the outer planets show us how life might persist in hidden refuges, even when surface conditions become hostile. Each of these examples expands our understanding of the boundaries of habitability, the conditions under which life can begin, persist, or fail. They're natural laboratories for studying planetary evolution, case studies in the various ways a world story can unfold. But perhaps the most important lesson they offer is about timescales and tipping points. Planetary changes that seem gradual from a human perspective can be catastrophically rapid from a geological one. Systems that appear stable can hide vulnerabilities that only become apparent when they're crossed. The challenge for any civilization that becomes aware of these dynamics is learning to think and act across the vast timescales on which planetary stability operates, while still functioning within the much shorter scales of individual lives and political systems. It requires a kind of temporal perspective that doesn't come naturally to minds evolved to focus on immediate threats and opportunities. Yet this perspective might be exactly what's needed to avoid joining the graveyard ourselves. To make choices today that account for their consequences, decades or centuries from now. To maintain the patience needed for solutions that might take generations to fully implement. In that sense, contemplating the possibility of failed worlds isn't an exercise in cosmic pessimism. It's an exercise in cosmic responsibility, a way of recognizing that our planet's current habitability isn't guaranteed, that it requires active maintenance, and that we've now become part of the system responsible for that maintenance. The graveyard of worlds, if it exists, doesn't judge us. It simply reminds us that the story isn't over yet, that the conditions allowing us to exist are both precious and precarious, and that how that story continues depends partly on choices we're making right now. The question of whether we're alone has haunted humanity since we first looked up at the stars. But there's another question, perhaps more unsettling, that we've only recently begun to ask with any scientific rigor. Not whether we're alone, but whether we're next. Every world has a lifespan, measured not in human years, or even in the rise and fall of civilizations, but in the slow breathing of geological epochs. Stars are born, burn bright, then fade or explode. Planets form from cosmic dust, develop their own unique characteristics, and eventually meet their end through processes both violent and gradual. What we're beginning to understand is that habitability itself has a lifespan too, one that can be cut short by forces both internal and external. Consider the delicate choreography required for a planet to remain in what scientists call the habitable zone. This isn't just about distance from a star, though that matters enormously. It's about maintaining that distance as the star itself evolves, gradually brightening over billions of years. A planet that starts out comfortably warm might eventually find itself being slowly cooked as its star ages, the habitable zone moving outward and leaving it behind. Even if a world manages to stay within the right temperature range, there are countless other factors that can tip the balance. The thickness of its atmosphere, the strength of its magnetic field, the activity of its core, the composition of its surface rocks, the presence or absence of large moons, the gravitational influence of giant planets elsewhere in the system. Each of these represents a potential point of failure, a way for habitability to slip away. What makes this particularly sobering is the timescales involved. A planet might remain stable and life-supporting for hundreds of millions of years, long enough for complex ecosystems to develop, for evolution to produce countless species, perhaps even for intelligence to emerge. But then something changes. the magnetic field weakens, allowing solar radiation to strip away the atmosphere. Volcanic activity increases, pumping too much carbon dioxide into the air. An asteroid impact triggers a cascade of climate effects that the planet's systems can't recover from. From our human perspective, these changes might seem gradual, unfolding over geological time. But from the perspective of a planetary system, they can be sudden tipping points, moments when a world crosses from habitable to uninhabitable with no way back. Mars offers us perhaps the clearest example of this process. Evidence suggests it once had a thicker atmosphere, warmer temperatures, and liquid water flowing across its surface. River valleys carved into its rocks, minerals that could only have formed in the presence of water, polar ice caps that hint at more dynamic climate cycles in the past. For a time, perhaps hundreds of millions of years, Mars might have been a place where life could have taken hold. But Mars is smaller than Earth, and smaller planets cool more quickly. As its core cooled, it lost the magnetic field that had protected its atmosphere from the solar wind. Without that protection, the thin Martian air was gradually stripped away into space. As the atmosphere thinned, surface pressure dropped, and liquid water could no longer remain stable. What had once been a potentially living world became the frozen desert we see today. The transformation wasn't immediate. It unfolded over millions of years, perhaps giving life time to adapt, to retreat to underground refuges, or to evolve in ways that might have allowed it to survive in increasingly harsh conditions. But eventually, the surface of Mars became uninhabitable by any standard we would recognize. If life ever existed there, it either went extinct or retreated so far underground that we haven't found it yet. Venus tells an even more dramatic story of planetary transformation. Similar in size to Earth, it may have started with conditions not entirely unlike our own. Some models suggest it could have had oceans for billions of years, with temperatures and atmospheric conditions that might have supported life. But Venus orbits closer to the Sun, receiving more solar energy than Earth does. At some point, perhaps gradually, perhaps more suddenly, Venus entered what's called a runaway greenhouse effect. As temperatures rose, more water evaporated into the atmosphere. Since water vapor is itself a greenhouse gas, this trapped even more heat, causing more evaporation in an accelerating cycle. Eventually, the oceans boiled away entirely. The water vapor was broken apart by solar radiation and lost to space, leaving behind an atmosphere of almost pure carbon dioxide under crushing pressure. Today, Venus is hot enough to melt lead, with surface pressures nearly 100 times greater than Earth's. Clouds of sulfuric acid swirl through its thick atmosphere. Any life that might once have existed there was obliterated so thoroughly that not even chemical traces remain detectable from our current vantage point. Both Mars and Venus represent cautionary tales about planetary evolution. They show us that worlds can start with promise and lose it through processes that, once begun, become irreversible. They also demonstrate that the factors determining a planet's fate aren't always obvious from the beginning. Venus and Earth formed from the same materials, in the same region of the solar system, yet their stories diverged completely. This raises uncomfortable questions about predictability. If we can't always tell from a planet's initial conditions whether it will remain habitable over geological time, how can we assess the long-term prospects for habitability elsewhere in the galaxy? How many worlds that appear promising today are actually already on trajectories toward uninhabitability? The more we study planetary evolution, the more we realize that stable habitability requires an extraordinary confluence of factors. It's not enough for a planet to be in the right place at the right time. It has to stay in the right place as conditions change around it. It has to maintain the right atmospheric composition as its star evolves. It has to avoid catastrophic impacts while still receiving enough smaller impacts to deliver water and organic compounds. It has to develop plate tectonics to recycle carbon and regulate climate, but not so much geological activity that the surface becomes uninhabitable. Each of these requirements represents a kind of evolutionary bottleneck that most worlds probably never pass through. The result is that the galaxy might be filled with planets that almost made it, worlds that came tantalizingly close to supporting long-term habitability, but ultimately fell short due to some combination of bad timing, bad luck, or the inherent instability of planetary systems. This perspective fundamentally changes how we think about the search for life. We're not just looking for worlds that currently show signs of biological activity. We're also looking for worlds that once did, planets whose atmospheric compositions or surface features reveal the chemical signatures of past life. These biosignatures might persist long after the life that created them has vanished, like fossils preserved in rock layers. Detecting such signatures would be both exciting and sobering. Exciting because they would prove that life can arise elsewhere, that Earth isn't unique in hosting biological processes. Sobering because they would also prove that life can end, that habitability isn't permanent, that the universe is littered with worlds that once lived but do so no longer. From this perspective, every living world becomes precious not because life is common, but because it's temporary. Every ecosystem, every species, every moment of biological complexity represents a temporary victory against the universe's tendency towards simplicity and decay. And every world that maintains these victories for billions of years is achieving something genuinely remarkable. The implications extend beyond astrobiology into our understanding of our own planet's future. Earth has maintained habitability for over 4 billion years, surviving multiple mass extinctions, dramatic climate shifts, and countless asteroid impacts. But this track record doesn't guarantee future success. The same forces that transformed Mars and Venus are still operating. The same potential tipping points still exist. Our planet's magnetic field has weakened and reversed many times in the past, though it has never completely disappeared during the age of complex life. Our climate has swung between ice ages and warmer periods, but has never entered a permanent snowball state or runaway greenhouse effect. Our atmosphere has changed composition dramatically, from the early carbon dioxide-rich air to the oxygen-rich mixture we breathe today, but has never been completely stripped away. Each of these represent near misses, moments when Earth could have joined the graveyard of worlds but didn't. The fact that we've avoided these fates so far is remarkable, but it doesn't make us immune to them in the future. We're still subject to the same physical processes that ended habitability elsewhere. What's different now is that we're aware of these processes. We can study them, model them, and potentially intervene in them. We have the capability to track asteroids and deflect them if necessary. We can monitor volcanic activity and climate changes. We're beginning to understand the complex feedback loops that maintain atmospheric stability. But awareness and capability aren't the same as action. Understanding the forces that could end Earth's habitability doesn't automatically protect us from them. It only gives us the opportunity to protect ourselves, if we choose to use it. This brings us to one of the most profound questions raised by the concept of failed worlds. If intelligence is rare in the universe, if conscious beings capable of understanding planetary processes are scattered thinly across space and time, then what responsibility do we bear for maintaining the conditions that allow intelligence to exist? Every civilization that becomes aware of its planet's fragility faces this choice. They can treat their world as a resource to be consumed, assuming that technological progress will always find solutions to any problems they create. Or they can treat it as a rare and precious system that requires careful stewardship to maintain over deep time. The graveyard of worlds suggests that this choice matters more than we might like to believe, that the universe doesn't guarantee the persistence of habitability, even on worlds that seem perfectly suited for life. That intelligence, once it emerges, becomes part of the planetary system, capable of either maintaining or destroying the conditions that allowed it to arise. From this perspective, our current moment in Earth's history is both ordinary and extraordinary. Ordinary because every living world faces challenges to its habitability, because the forces that could end our story are the same ones that have ended countless others. Extraordinary because we're among the first generations of any species on Earth to recognize these forces and potentially do something about them. The weight of that recognition is something no other species has ever carried. Previous mass extinctions happened to life on Earth, but they weren't caused by life understanding and then mismanaging the planetary systems it depended on. We're in uncharted territory, not just for our own species, but for the concept of intelligence itself. Whether we navigate this territory successfully will determine not just our own future, but the future of consciousness itself on Earth. If we join the graveyard of worlds, it won't just be the end of human civilization. It will be the end of the only known example of matter organizing itself into forms capable of contemplating their own existence. That possibility should give us pause, not because it makes our situation hopeless, but because it makes our choices matter in ways they never have before. We're not just deciding the fate of our own generation or even our own species. We're deciding whether this rare experiment in cosmic self-awareness continues or becomes another silent entry in the galaxy's archive of lost worlds. The silence of space carries within it countless stories we'll never hear. When we point our most powerful telescopes toward distant star systems, we see snapshots frozen in time. A planet orbiting too close to its star, its surface molten and uninhabitable. Another world locked in eternal winter, so far from its sun that any atmosphere has long since frozen solid. Gas giants with crushing gravity and toxic storms that make them utterly hostile to any form of life we can imagine. But what we can't see from these vast distances are the stories of transition. The worlds that might have spent millions of years in perfect balance before something shifted. The planets that once had blue skies and flowing water, whose surfaces are now cracked and barren. The places where complex chemistry might have been on the verge of becoming biology before some cosmic accident reset the clock entirely. These hidden stories matter because they remind us that planetary evolution isn't a straight line towards success or failure. It's a maze of possibilities, most of which lead to dead ends. A world might maintain perfect conditions for 1 billion years, long enough for evolution to produce wonders we can barely imagine, only to lose everything in a geological instant when the wrong combination of circumstances aligns. Consider the sheer number of variables involved in keeping a planet habitable. The star must remain stable, not prone to the violent flares that can strip away atmospheres, or the gradual dimming that leaves worlds frozen. The planet's orbit must stay within that narrow zone, where water remains liquid, not drifting inward towards scorching heat or outward into permanent ice. The internal structure must generate enough heat to drive geological processes, but not so much that the surface becomes a volcanic hellscape. Beyond these basics, there are subtler requirements that we're only beginning to understand. The right amount of water, distributed in ways that create weather patterns capable of distributing heat around the globe. An atmosphere thick enough to hold warmth and protect the surface from radiation, but not so dense that it creates crushing pressure or runaway greenhouse effects. Chemical cycles that can regulate themselves over millions of years, buffering against changes that would otherwise destabilize the entire system. Each of these factors can change over time, and those changes interact with each other in ways that are difficult to predict. A slight warming trend might trigger the release of greenhouse gases from melting ice or thawing soil, accelerating the warming in a feedback loop that becomes impossible to stop. A weakening magnetic field might allow more cosmic radiation to reach the surface, damaging the atmospheric chemistry that maintains breathable air. The mathematics of these interactions are staggering. Small changes in any one factor can cascade through the entire planetary system, sometimes stabilizing it in new configurations, sometimes driving it towards states that can no longer support complex life. The fact that Earth has navigated these cascading changes for billions of years without crossing any irreversible thresholds is genuinely remarkable. But remarkable doesn't mean guaranteed. Every day, our planet continues to walk the tightrope between habitability and the various forms of uninhabitability that have claimed other worlds. Solar radiation continues to gradually strip away our atmosphere, though at a rate so slow that other processes can compensate. Our magnetic field continues to fluctuate, sometimes weakening to levels that allow more cosmic radiation to penetrate. Volcanic activity continues to inject gases into our atmosphere, sometimes in quantities that could alter our climate if other factors weren't working to balance them out. The difference between Earth and the failed worlds scattered throughout the galaxy might be nothing more than timing. We happen to exist during a period when all these balancing acts are working in our favor. Mars might have been habitable for just as long as Earth has been, but during a different epoch in solar system history. Venus might have supported life for billions of years before its proximity to the Sun finally triggered the runaway processes that turned it into a furnace. This temporal perspective is crucial for understanding our place in cosmic history. We often think of Earth's current state as normal, as the way things are supposed to be. But normality, in planetary terms, is an illusion. What we call normal is actually a specific set of conditions that happen to exist right now, maintained by processes that are themselves temporary. The oxygen in our atmosphere, for instance, is not a natural feature of planetary evolution. It's a waste product of photosynthesis, accumulated over billions of years by organisms that learned to harness sunlight. Without constant replenishment by living things, atmospheric oxygen would gradually disappear, consumed by chemical reactions with rocks and metals on the surface. The air we breathe exists only because life continues to produce it. Similarly, the carbon dioxide levels that help maintain our planet's temperature are regulated by a complex dance between geological processes, ocean chemistry, and biological activity. Too much CO2 and we risk a runaway greenhouse effect like Venus experienced. Too little and we could slide into a permanent ice age. The fact that this balance has held for so long is not the result of some planetary design, but of countless feedback mechanisms that have evolved over deep time. These mechanisms are robust, but they're not infinitely so. Push them too far or too fast, and they can break down entirely. When that happens, a planet doesn't gradually slide toward uninhabitability. It can flip suddenly into a new state, one that may be stable in its own way, but utterly hostile to the forms of life that existed before. The geological record shows us that Earth has experienced several near misses with such transitions, periods when the planet came close to freezing entirely, with ice extending almost to the equator. Times when volcanic activity pumped so much CO2 into the atmosphere that global temperatures soared and ocean chemistry changed dramatically. Episodes when asteroid impacts created global winter conditions that lasted for years. In each case, the planet eventually returned to a state that could support complex life. But there's no guarantee that recovery was inevitable. A slightly different set of circumstances, a bit more volcanic activity, or a somewhat larger asteroid, and Earth might have crossed a threshold from which it never returned. The sobering reality is that we have no way of knowing how close we came to permanent failure during these events. The difference between recovery and irreversible collapse might have been measured in degrees of temperature change or percentages of atmospheric composition. We survived, but countless other worlds facing similar challenges probably didn't. This brings us to a fundamental question about the nature of habitability itself. Is it an inherently unstable state that requires constant maintenance to persist? Or is it naturally stable, requiring extreme circumstances to disrupt? The evidence from our own solar system suggests it's closer to the former. Habitability appears to be a temporary arrangement, a narrow window of conditions that can be maintained for a while, but will eventually close. Mars and Venus both show signs of having had more Earth-like conditions in their past. The fact that both lost those conditions through different mechanisms and on different timescales suggests that maintaining habitability over geological time is genuinely difficult. It requires not just the right starting conditions, but the ability to adapt to changing circumstances without crossing irreversible thresholds. For worlds that develop intelligent life, this creates a unique challenge. Unlike other forms of life, intelligence has the potential to either accelerate the loss of habitability or extend it far beyond its natural lifespan. Civilizations can alter planetary systems faster than natural processes, potentially triggering the kinds of rapid changes that lead to irreversible shifts. But they can also monitor these systems, understand their dynamics, and potentially intervene to maintain stability. The question is whether intelligence typically emerges early enough in a planet's habitable lifetime to make a difference, and whether civilizations that do emerge are wise enough to use their capabilities responsibly. If the galaxy is indeed filled with failed worlds, some of those failures might be the result of intelligent species that gained the power to alter planetary systems before they gained the wisdom to manage them sustainably. This possibility adds another layer to the graveyard of worlds, not just planets that failed due to natural processes, but worlds that were pushed into uninhabitability by their own inhabitants. Civilizations that grew too quickly, consumed resources too rapidly, or altered their atmospheres too dramatically to maintain the conditions that had allowed them to evolve in the first place. From our current vantage point, it's impossible to know which category Earth might fall into. We've developed the capability to alter planetary systems on a massive scale, but we're still learning to understand the consequences of those alterations. We can measure the changes we're making to atmospheric composition, ocean chemistry, and global climate, but predicting how those changes will interact with natural processes over long timescales remains extraordinarily challenging. What we do know is that the changes we're making are happening at a pace that's unprecedented in planetary history. At least during the age of complex life, previous shifts in atmospheric composition or global climate typically unfolded over millions of years, giving ecosystems time to adapt and planetary systems time to find new equilibria. The changes we're driving are happening in decades or centuries, faster than most natural feedback mechanisms can respond. This speed matters because it determines whether Earth's planetary systems can maintain the kind of stability that has characterized our world for billions of years. Rapid changes can overwhelm the buffering mechanisms that have kept our planet habitable, pushing us toward the kinds of irreversible transitions that transformed Mars and Venus into the worlds we see today. But speed also creates opportunity. Because we're causing these changes, we potentially have the ability to control them. Unlike previous life forms that could only react to planetary changes, we can anticipate them, model their consequences, and take action to prevent or mitigate them. We have the theoretical capability to manage Earth's planetary systems in ways that maintain habitability indefinitely. Whether we'll actually use that capability remains to be seen. Managing planetary systems requires thinking and acting on timescales that don't come naturally to human societies. It requires making sacrifices in the present to prevent problems that might not manifest for decades or centuries. It requires global cooperation on a scale that we've never achieved before. The alternative, however, is potentially joining the graveyard of worlds, not necessarily through dramatic collapse, but through the gradual erosion of the conditions that make complex life possible. A slow slide toward a planet that can no longer support the ecosystems we depend on, the climate patterns we've adapted to, or the chemical cycles that maintain breathable air and drinkable water. The choice isn't binary. Between thriving habitability and complete sterility lies a range of possible futures. Some might support simple life but not complex ecosystems. Others might maintain pockets of habitability while losing it globally. Still others might remain technically habitable but become so unstable that complex civilization becomes impossible to maintain. Each of these outcomes would represent a different kind of failure, a different way of joining the cosmic collection of worlds that once held promise but couldn't maintain it. The question isn't just whether we'll avoid the most extreme scenarios, but whether we'll preserve the kind of stable, predictable habitability that allowed intelligence to emerge in the first place. This perspective transforms how we think about environmental challenges. They're not just problems that affect human welfare or economic systems. They're tests of whether we can maintain the planetary conditions that make our existence possible. Every degree of temperature change, every shift in ocean chemistry, every alteration of atmospheric composition is a step either toward or away from the long-term habitability that distinguishes living worlds from the silent majority. The Graveyard of Worlds isn't just a collection of cautionary tales. It's a reminder that habitability is an achievement, not a given. Every day that Earth continues to support complex life is another day that we've successfully navigated the challenges that have defeated countless other worlds. Every generation that inherits a stable climate and breathable air is receiving a gift that most planets in the galaxy have never been able to provide. But gifts can be squandered as easily as they can be preserved. The same intelligence that allows us to understand our planet's fragility also gives us the power to either protect or destroy it. We've become participants in the cosmic experiment of habitability, no longer just subjects of planetary processes, but agents capable of shaping them. How that experiment turns out will depend on choices we're making right now. Whether we join the Graveyard of Worlds or extend Earth's remarkable run of habitability for millions of years to come. Whether we become another cautionary tale scattered among the stars, or prove that intelligence can indeed learn to maintain the conditions that created it. The universe won't judge us either way. It will simply record the outcome in the slow accumulation of geological layers, the gradual evolution of atmospheric composition, the presence or absence of the chemical signatures that indicate a living world. Future explorers, if any exist, will read that record and draw their own conclusions about what happened here during this brief moment when matter had organized itself into forms capable of contemplating their own existence. For now, we remain among the living worlds. Our story continues to unfold, our planet continues to breathe, and our place in the cosmic experiment of habitability remains unresolved. The graveyard waits patiently, as it always has, neither welcoming nor rejecting new members, simply existing as a reminder that every world story eventually comes to an end, and that how long that story lasts depends on forces both beyond our control and entirely within it. The question of whether we're alone in the universe has captivated humanity for generations, but there's a darker version of that question that's only recently begun to emerge from the shadows of scientific speculation. Not just whether other civilizations exist, but whether they still exist. Whether the signals we're listening for might be echoing across empty space from worlds that fell silent long before our radio telescopes turned skyward. When we imagine contact with extraterrestrial intelligence, we typically picture it happening in real time. A signal detected today, sent by beings who are alive and active somewhere among the stars. But the vast distances between star systems mean that any communication we receive would already be ancient by the time it reaches us. A message from a civilization 1,000 light years away would carry news that's 1,000 years old by the time we hear it. This creates an unsettling possibility. We might detect clear evidence of intelligence, unambiguous proof that we're not alone, only to realize that we're listening to the voices of the dead. That somewhere in the galaxy, perhaps many somewheres, civilizations rose to prominence, developed technology, sent signals into space, and then vanished before those signals completed their journey to Earth. The mathematics of cosmic distances and the lifespan of civilizations make this scenario not just possible, but probable. If technological civilizations typically last for thousands or tens of thousands of years, but their signals take millions of years to cross the galaxy, then most of the intelligence we might detect would be archaeological rather than contemporary. We'd be cosmic archaeologists, piecing together evidence of societies that existed when our own planet was still dominated by simpler life forms. This temporal disconnect adds another dimension to the graveyard of worlds. Not just planets that lost their habitability through natural processes, but worlds where intelligence emerged, flourished for a time, and then disappeared through mechanisms we can only guess at. Some might have fallen victim to the same planetary instabilities that claimed Mars and Venus. Others might have destroyed themselves through warfare, environmental collapse, or technologies they couldn't control. The fossil record of our own planet offers sobering precedents for how quickly dominance can end. Species that ruled their ecosystems for millions of years vanished in geological instants when conditions changed. The dinosaurs dominated terrestrial ecosystems for over 160 million years, yet they disappeared so completely that we only discovered their existence in the past few centuries. If that can happen to biological dominance, it can certainly happen to technological dominance. But civilizations face risks that purely biological species never encountered. The same intelligence that allows them to manipulate their environment also gives them the power to destabilize it. Nuclear weapons, climate modification, genetic engineering, artificial intelligence, each represents a capability that could either extend a civilization's lifespan or end it prematurely. The speed at which these technologies develop might be crucial. If civilizations typically discover dangerous capabilities before they develop the wisdom to manage them safely, then the galaxy might be littered with worlds where intelligence burned brightly for a few centuries before extinguishing itself. From the perspective of cosmic time, such civilizations would be brief flickers, barely noticeable against the slow background of planetary evolution. This possibility transforms how we interpret the silence we hear when we listen to the stars. The absence of obvious signals from other civilizations might not mean that intelligence is rare. It might mean that intelligence is typically short-lived, or that it tends to destroy the very conditions that allowed it to emerge in the first place. Consider the energy requirements of a technological civilization. As societies become more complex, they demand increasing amounts of resources and energy. This growth can be sustainable for a time, but every planet has limits. Finite supplies of metals, fossil fuels, fresh water, arable land. A civilization that grows too quickly or consumes too efficiently might exhaust the resources it depends on before it can transition to more sustainable alternatives. Earth's own history provides examples of this dynamic on smaller scales. Civilizations that overexploited their local environments, leading to soil depletion, deforestation, or the collapse of the ecosystems they depended on. The difference now is that our civilization is global rather than local. If we overexploit Earth's resources or destabilize its climate, there's no neighboring region to expand into, no backup environment to fall back on. The same technologies that give us unprecedented power over our environment also create unprecedented vulnerabilities. Global communication networks that can be disrupted by solar storms or cyber attacks. Food distribution systems that span continents but can be severed by conflicts or natural disasters. Financial systems so interconnected that local failures can trigger worldwide collapse. These vulnerabilities might be universal features of advanced civilizations. The complexity that makes them powerful also makes them fragile. The interconnections that increase their efficiency also create pathways for failure to propagate throughout the entire system. A civilization might reach heights of technological achievement only to discover that it had built itself into a configuration so delicate that minor disruptions could bring down the whole structure. From this perspective, the transition from a pre-technological to a technological civilization might be one of the most dangerous phases in the evolution of intelligence. Species that successfully make this transition might join the ranks of long-lived galactic civilizations. Those that don't might add their worlds to the graveyard, places where intelligence emerged but couldn't sustain itself long enough to spread beyond its home planet. The search for extraterrestrial intelligence takes on a different character when viewed through this lens. We're not just looking for contemporary civilizations that might be trying to communicate with us. We're also, perhaps primarily, looking for the remains of civilizations that tried to communicate in the past. Archaeological evidence of intelligence that might have vanished before our own species even existed. This archaeological approach might actually be more promising than searching for active signals. The remains of a technological civilization could persist long after the civilization itself disappears. Artificial structures might be detectable for thousands or millions of years. Changes to a planet's atmosphere or surface might remain visible across even greater timescales. We might find evidence of intelligence in places where no intelligence currently exists. But detection is only the first challenge. Even if we found clear evidence of a vanished civilization, understanding what happened to it would be extraordinarily difficult. We'd be trying to reconstruct the final chapters of a story using only the physical evidence left behind, without access to the historical records, cultural context, or decision-making processes that led to the outcome. Did they destroy themselves through warfare? Exhaust their planet's resources? Trigger an environmental collapse they couldn't reverse? Fall victim to a natural disaster they couldn't prevent or predict? Or did they simply evolve into something so different from their original form that we wouldn't recognize their descendants as the same species? Each of these possibilities would leave different traces, different patterns of evidence that might be detectable from interstellar distances. Learning to read these patterns, to distinguish between various forms of civilizational collapse, might become one of the most important skills for anyone hoping to understand the fate of intelligence in the universe. The implications for our own future are profound. If the galaxy is indeed filled with the remains of civilizations that couldn't navigate the challenges of technological development, then we're not just facing problems that are unique to Earth or to humanity. We're confronting universal challenges that every intelligent species must solve if they want to survive their own success. This realization could be either reassuring or terrifying, depending on your perspective. Reassuring because it means we're not uniquely flawed or uniquely endangered. The problems we're grappling with, climate change, resource depletion, technological risk, are probably universal features of the transition from biological to technological intelligence. Terrifying because it means these problems might be harder to solve than we hope, given that so many other civilizations appear to have failed to solve them. But there's another possibility, one that offers a different kind of hope. Maybe some civilizations do successfully navigate these challenges. Maybe they develop the wisdom to manage their power responsibly, the foresight to avoid the pitfalls that claim others, the cooperation needed to address problems that span generations. Maybe they learn to live within their planet's means while still maintaining the technological capabilities that make them recognizably intelligent. Such civilizations might be rare, but they wouldn't necessarily be detectable. A society that achieved genuine sustainability might have a very small footprint compared to one that was rapidly expanding and consuming resources. They might deliberately limit their energy use, their population growth, their impact on their environment. From our perspective, they might be nearly invisible, hidden among the background of natural planetary processes. This creates a selection bias in our search for extraterrestrial intelligence. The civilizations we're most likely to detect might be the ones that are burning brightest, consuming the most energy, making the most dramatic changes to their environments. In other words, the ones that are most likely to burn out quickly. The successful, long-lived civilizations might be precisely the ones that are hardest to find. If this is true, then the silence we hear from the stars might not reflect the absence of intelligence, but the presence of mature intelligence that has learned to live quietly. The graveyard of worlds might coexist with a hidden community of survivors, civilizations that solved the problems that destroyed their neighbors, and now exist in a state of equilibrium that makes them effectively invisible to our current detection methods. This possibility suggests that the search for extraterrestrial intelligence might need to evolve beyond looking for obvious technological signatures. Instead of searching for civilizations that are broadcasting their presence across the galaxy, we might need to learn to detect the subtle signs of intelligence that has achieved sustainability. The careful management of planetary resources, the maintenance of stable atmospheric compositions, the presence of complex but balanced ecosystems. These signatures would be much harder to detect and interpret than the clear signals we typically search for. They would require us to develop new ways of analyzing planetary systems, new methods for distinguishing between natural processes and intelligent management. We'd be looking for intelligence that has learned to mimic nature so closely that it's almost indistinguishable from it. The challenge of detecting sustainable civilizations reflects a broader challenge in understanding the long-term evolution of intelligence. We tend to assume that technological development follows a trajectory of increasing energy use, increasing environmental impact, increasing visibility. But that trajectory might be characteristic only of young, immature civilizations that haven't yet learned to control their growth. Mature civilizations might follow very different trajectories. They might focus on efficiency rather than expansion, on stability rather than growth, on integration with their environment rather than domination over it. These civilizations might be more successful in the long run, but they would also be much harder for us to recognize as intelligent. This creates a paradox in our search for cosmic company. The civilizations we're most likely to find might be the ones that are least likely to survive. The ones that are most likely to survive might be the ones we're least likely to find. We might be looking for intelligence in all the wrong places, focusing on the dramatic signatures of civilizations that are already doomed while missing the subtle signs of those that have learned to endure. The graveyard of worlds in this view isn't just a collection of failed experiments. It's also a filter, a selection process that weeds out civilizations that can't learn to live within their means. The survivors might be out there, quietly maintaining the conditions that allow intelligence to persist. But they've learned to do so without attracting the attention of younger, louder civilizations like ourselves. Whether we'll eventually join their ranks or add our own world to the graveyard depends on whether we can learn the lessons that the failed civilizations apparently couldn't master, whether we can develop the wisdom to match our power, the foresight to avoid the traps that claimed others, the cooperation to address challenges that span generations and cross all traditional boundaries. The universe watches these experiments in intelligence with the same indifference it shows to the formation of stars or the collision of galaxies. Success and failure are equally natural outcomes, equally valid endpoints in the story of how matter organizes itself into increasingly complex forms. But for those of us caught in the middle of the experiment, the outcome matters in ways that transcend any cosmic perspective. We're not just deciding whether humanity survives or disappears. We're deciding whether Earth remains among the living worlds or joins the silent majority, whether consciousness continues to exist in this particular corner of space and time, or whether it flickers out and leaves behind only the geological traces of what once was. The weight of that choice is something no previous generation has had to carry, but it's also an opportunity that no previous generation has had the chance to seize. We stand at a threshold that most worlds apparently never reach, the point where intelligence becomes capable of consciously directing its own evolution and that of its planet. What happens next will become part of the permanent record, written in stone layers and atmospheric compositions that will persist long after any memory of our individual lives has faded. Whether that record tells the story of another failed experiment or of intelligence that learned to transcend the limitations that claimed so many others before us. The silence between the stars isn't empty. It carries within it the echo of countless experiments, worlds that flickered into complexity and then faded back into cosmic quiet. When we listen for signals from other civilizations, we're not just searching for contemporary voices. We're archaeological detectives, sifting through transmissions that might have begun their journey across space when Earth was still a molten ball of rock, sent by minds that turned to dust long before the first human ever looked up at the night sky. This temporal displacement changes everything about how we understand our search for cosmic companionship. The universe operates on scales that make human history seem like a single breath. Light from distant stars takes millions of years to reach us, carrying information about events that happened when our planet looked nothing like it does today. Any signal we detect from an extraterrestrial civilization would be similarly ancient, a message in a bottle thrown into an ocean of space by beings who might have vanished before it ever reached our shores. Consider the mathematics of this cosmic archaeology. If a technological civilization typically lasts for 10,000 years, but their radio signals take 1,000,000 years to cross the galaxy, then for every civilization we might detect that's still alive, there could be 100 whose voices reach us from beyond the grave. We might spend decades decoding a message, celebrating the proof that we're not alone, only to realize we're reading the final transmission from a world that went silent millennia before our ancestors discovered fire. This possibility adds a haunting dimension to the graveyard of worlds. Not just planets that lost their habitability through natural processes, but worlds where intelligence emerged, reached toward the stars, and then fell back into darkness for reasons we can only speculate about. Each failed civilization would leave behind its own unique signature of collapse, written in the chemical composition of atmospheres, the distribution of artificial materials, the sudden absence of the complex patterns that indicate active management of planetary systems. The search for these signatures requires us to think like cosmic forensic investigators. We look for isotope ratios that suggest nuclear technology, atmospheric compositions that hint at industrial activity that suddenly stopped, surface features that might be the remains of cities now buried under millions of years of sediment and erosion. These traces would be far subtler than the dramatic signals we typically imagine receiving from active civilizations. But subtlety doesn't mean insignificance. A world that once supported a technological civilization would bear permanent scars from that experience. The mining of rare metals leaves geological signatures that persist for billions of years. The burning of fossil fuels alters atmospheric chemistry in ways that can be detected long after the last factory has crumbled to dust. Even the redistribution of elements through manufacturing and construction creates patterns that don't occur naturally. The challenge lies in distinguishing these artificial signatures from the countless natural processes that can create similar effects. Volcanic activity can alter atmospheric composition. Asteroid impacts can redistribute metals across a planet's surface. Biological processes can create complex chemical patterns that might be mistaken for industrial activity. Learning to read the difference between natural and artificial signatures requires understanding planetary evolution in exquisite detail. This is where the failed worlds in our own solar system become invaluable laboratories. Mars and Venus offer us case studies in planetary collapse, examples of worlds that lost their habitability through processes we can observe and measure. If either planet once supported life, even simple microbial life, that experience would have left traces we're only beginning to learn how to detect. The search for these traces has already begun in earnest. Rovers on Mars analyze soil samples for organic compounds that might indicate past biological activity. Orbiters study the planet's atmospheric composition for gases that could only be produced by living processes. Each measurement adds another piece to the puzzle of whether Mars was once alive, and, if so, what caused that life to end. But Mars represents only one possible path to failure. A world might lose its habitability through the gradual weakening of its magnetic field, as appears to have happened there. Or it might suffer a runaway greenhouse effect like Venus experienced. Or it might face challenges we haven't yet imagined. Processes that could end a planet's ability to support complex life through mechanisms we've never observed. The diversity of possible failure modes means that the graveyard of worlds might contain an extraordinary variety of stories. Some planets might have been struck down in their prime by asteroid impacts or nearby supernovae. Others might have slowly declined over millions of years as their stars evolved beyond the narrow range of energy output that maintains habitability. Still others might have been victims of their own success, civilizations that grew too quickly and consumed their world's resources faster than sustainable alternatives could be developed. Each type of failure would leave its own distinctive signature, its own pattern of evidence that could be detected by sufficiently advanced instruments. Learning to recognize these patterns, to distinguish between different causes of planetary death, might become one of the most important skills in astrobiology, not just for understanding what happened to other worlds, but for recognizing the warning signs that might appear in our own planet's future. The temporal aspect of this search creates another layer of complexity. The evidence we're looking for might exist at different stages of decay. A civilization that collapsed 1 million years ago would leave different traces than one that vanished 1 billion years ago. Atmospheric signatures might fade over time, while geological evidence could persist much longer. Understanding these decay rates is crucial for interpreting whatever evidence we might find. There's also the question of how civilizations end. Popular imagination tends to focus on dramatic scenarios, nuclear wars or asteroid impacts that wipe out entire species in a matter of days or years. But the more we understand about planetary systems and the challenges of maintaining technological civilizations, the more likely it seems that most failures happen gradually. A civilization might slowly exhaust the resources it depends on, leading to economic collapse and social fragmentation. Climate changes, whether natural or artificial, might make agriculture increasingly difficult until food systems break down entirely. Political instability might prevent the long-term cooperation needed to address planetary-scale challenges. In each case, the end result would be the same: a world that once supported complex technological activity returning to a simpler state, but the process could unfold over centuries rather than moments. These gradual collapses might be harder to detect from interstellar distances, but they could also leave more complex archaeological records. A civilization that declined slowly might have time to adapt, to preserve some knowledge, to leave behind intentional records of what happened and why. We might find not just the physical evidence of technological activity, but actual messages, warnings left by civilizations that saw their own end approaching and wanted to share their experience with whoever might come after. The possibility of finding such messages adds urgency to our search for signs of vanished civilizations. These wouldn't just be archaeological curiosities, but practical guides for avoiding similar fates. A civilization that successfully identified the causes of its own collapse might leave behind invaluable insights about the challenges that all technological species face. But there's another possibility that's perhaps even more intriguing. What if some civilizations don't collapse at all, but instead learn to live so sustainably that they become nearly invisible to our current detection methods? What if the galaxy contains not just a graveyard of failed worlds, but also a hidden community of successful ones that have learned to maintain their technological capabilities without the dramatic energy consumption and environmental impact that characterize young civilizations? These mature civilizations might have solved the problems that destroyed their neighbors. They might have developed fusion power that provides clean energy without depleting planetary resources. They might have learned to recycle materials so efficiently that mining becomes unnecessary. They might have achieved population stability that eliminates the pressure for exponential growth. They might even have learned to manage their planetary climate so skillfully that their worlds remain stable for millions of years. Such civilizations would be extraordinarily difficult to detect using our current methods, which focus on finding the obvious signatures of high-energy technological activity. A truly sustainable civilization might use its energy so efficiently that it produces minimal waste heat. It might manage its industrial processes so cleanly that it produces no atmospheric pollution. It might integrate its cities so seamlessly into natural ecosystems that they are invisible from space. This creates a profound selection bias in our search for extraterrestrial intelligence. The civilizations we're most likely to find might be the ones that are burning brightest and fastest, consuming resources at unsustainable rates, pumping waste products into their atmospheres, fundamentally altering their planetary environments. In other words, the civilizations most likely to destroy themselves. The successful civilizations, the ones that have learned to live within their planetary means, might be the ones that are hardest to find. They might exist in a state of dynamic equilibrium with their environments, maintaining complex technological capabilities while producing minimal detectable signatures. From our perspective, they might be effectively camouflaged, indistinguishable from the natural background processes of their worlds. This possibility suggests that the apparent silence of the galaxy might not reflect the absence of intelligence, but rather the presence of mature intelligence that has learned to live quietly. The graveyard of worlds might coexist with a network of survivor civilizations that communicate with each other using methods we haven't yet learned to detect, sharing knowledge and resources while remaining invisible to younger species like ourselves. If this hidden community exists, then our current search strategies might be fundamentally flawed. Instead of looking for civilizations that are advertising their presence across the galaxy, we might need to learn to detect the subtle signs of intelligence that has achieved true sustainability. We might need to look for planets that are too stable, too well balanced, too perfectly managed to be entirely natural. The challenge would be enormous. Natural planetary systems can achieve remarkable stability through purely physical and chemical processes. Distinguishing between a naturally stable world and one that's being carefully managed by an invisible civilization would require understanding planetary evolution with extraordinary precision. We'd need to know exactly what a planet should look like based on its size, composition, age, and stellar environment, and then look for deviations from that expected state that might indicate intelligent intervention. Even then, we might miss civilizations that have learned to manage their world so skillfully that their intervention is undetectable. The most successful civilizations might be those that have learned to work with natural processes rather than against them, guiding planetary evolution so subtly that the results appear entirely natural. This perspective transforms our understanding of what success might look like for a technological civilization. Instead of the dramatic expansion into space that science fiction often portrays, true success might involve learning to live permanently and sustainably on a single world, maintaining technological capabilities while preserving the planetary systems that support them. Such civilizations might never feel the need to colonize other stars because they've learned to find fulfillment within the bounds of their home worlds. They might develop their arts, sciences, and philosophies to extraordinary heights, while maintaining populations and resource consumption at levels their planets can support indefinitely. They might represent the ultimate expression of intelligence, minds that have learned to thrive within limits rather than constantly seeking to transcend them. From this perspective, our current trajectory as a species becomes deeply concerning. We're following the path of rapid growth, increasing energy consumption, and expanding environmental impact that might be characteristic of civilizations that don't survive their technological adolescence. We're burning bright and fast, exactly like the civilizations we're most likely to detect and most likely to find in the graveyard of worlds. The question becomes whether we can learn to change course before it's too late, whether we can develop the wisdom to match our power, the foresight to avoid the traps that claimed so many others, the discipline to choose sustainability over growth when the two come into conflict, whether we can join the ranks of civilizations that learned to live quietly and permanently, or whether we'll add our own world to the collection of promising experiments that ultimately failed. The universe offers no guidance on which path we should choose. It records the outcomes with equal indifference, preserving the geological signatures of both success and failure for future archaeologists to discover and interpret. But for us, caught in the middle of this cosmic experiment, the choice carries weight that transcends any individual life or generation. We're not just deciding our own fate, but the fate of consciousness itself in this corner of space and time. If we fail, we become another entry in the graveyard of worlds, another cautionary tale written in stone and atmospheric composition. If we succeed, we might join a community we've never detected. Civilizations that learn to transcend the limitations that destroyed their neighbors. Either way, our choice will become part of the permanent record. A message to whatever intelligences might arise in the future about what happened when matter briefly organized itself into forms capable of contemplating their own existence. Whether that message tells the story of wisdom or folly, success or failure, depends on decisions we're making right now, in this moment when our planet still breathes and our future remains unwritten. The mathematics of survival operate on scales that dwarf human comprehension. When we consider the age of the universe, the number of stars, the countless planets that have formed and evolved over billions of years, the numbers become so large they lose meaning. But within those vast statistics lies a more intimate calculation, one that determines whether any given world joins the community of survivors or becomes another silent member of the cosmic graveyard. For Earth, that calculation is still in progress. We exist in a moment of profound uncertainty, balanced on the edge between futures we can barely imagine. On one side lies the path toward sustainability, toward learning to live within our planet's means while maintaining the technological capabilities that define our species. On the other lies the trajectory that so many other worlds appear to have followed, toward overconsumption, environmental collapse, and the eventual silence that marks the end of complex civilization. The choice isn't ours alone to make. It's embedded in the decisions of billions of individuals, the policies of hundreds of governments, the innovations of countless scientists and engineers, the wisdom or folly of institutions that will outlive any of us as individuals. But it's also embedded in physical laws and planetary systems that operate according to their own logic. Regardless of our preferences or intentions, we can influence the outcome, but we can't control it entirely. The same forces that transformed Mars into a frozen desert and Venus into a furnace are still operating. The same potential for runaway climate change, atmospheric loss, and ecological collapse that claimed other worlds continues to exist. Our intelligence gives us the ability to recognize these dangers and potentially avoid them, but it doesn't make us immune to them. This recognition should inspire neither despair nor complacency, but rather a kind of cosmic humility. We're part of a vast experiment in the evolution of complexity, one that has been running for billions of years and will continue long after our sun burns out. Our role in that experiment is both insignificant and crucial, a single data point that nonetheless carries within it the entire future of consciousness in our local region of space and time. The graveyard of worlds reminds us that we're not the first to face these challenges, and we won't be the last. Somewhere among the stars lie the remains of civilizations that grappled with the same questions we're grappling with now. Some of them might have found answers we haven't discovered yet. Others might have failed in ways that could teach us what to avoid. But their stories are largely lost to us, written in languages of chemistry and geology that we're only beginning to learn to read. We're left to figure out the puzzle of long-term survival, mostly on our own, guided only by the physical laws that govern planetary evolution and the examples of success and failure we can observe in our immediate cosmic neighborhood. The silence of space carries within it both warning and promise. Warning because it suggests that most experiments in intelligence end in silence. Promise because that silence might hide communities of survivors who learn to transcend the limitations that destroyed their neighbors. We won't know which interpretation is correct until we either join the ranks of the silent or learn to detect the subtle signatures of civilizations that achieved genuine sustainability. For now, we remain among the living worlds, still breathing, still growing, still reaching toward futures we can envision but not guarantee. Our place in the cosmic story remains unwritten. Our final chapter still decades or centuries away from being recorded in the permanent archive of geological time. But every day we continue to exist as a technological civilization is another day we've successfully navigated the challenges that ended so many other experiments in intelligence. Every generation that inherits a stable climate and a functioning biosphere is receiving a gift that most worlds in the galaxy have never been able to provide. Whether we'll continue to receive that gift or whether we'll squander it through choices we're making right now remains the most important question our species has ever faced. The universe watches our experiment with the same patient indifference it shows to the formation of stars and the collision of galaxies. But for us, caught in the middle of the story, the outcome matters in ways that transcend any cosmic perspective. We are both observers and participants in the greatest experiment ever conducted, the attempt of matter to understand itself through the emergence of consciousness. Whether that experiment continues or joins the silent archives of failed worlds depends on our ability to learn from the examples around us, to recognize the warning signs before they become irreversible, and to make choices that honor both the rarity of our situation and the responsibility it entails. The graveyard of worlds awaits, patient and eternal. But so does the possibility of joining something greater, a community of minds that learn to survive their own success and continue the cosmic conversation that began when the first stars ignited in the darkness. Which future we'll inhabit remains to be seen, but the choice, for now, is still ours to make. The question of whether we're destined to join that graveyard brings us face to face with something even more unsettling than the possibility of failure. It forces us to confront the nature of success itself and whether the very qualities that make intelligence possible might also make it inherently self-destructive. Consider what intelligence actually is at its core. It's the ability to manipulate the environment in ways that serve immediate needs, to solve problems through the application of knowledge and tools. But intelligence also creates problems that didn't exist before. No other species has ever had to worry about nuclear weapons or climate change or artificial intelligence that might surpass its creators. These are uniquely intelligent problems, challenges that emerge directly from the same capabilities that we consider our greatest achievements. This creates what we might call the intelligence paradox. The more successful a species becomes at manipulating its environment, the more complex and potentially dangerous that environment becomes. Early humans used fire to cook food and stay warm, but they also started forest fires. We developed agriculture to feed larger populations, but we also began the process of soil depletion and ecosystem simplification that continues today. We harnessed fossil fuels to power industrial civilization, but we also began altering our planet's climate in ways we're still learning to understand. Each step forward in our technological capabilities has been accompanied by new categories of risk, new ways for intelligence to threaten the very conditions that allowed it to emerge. And the pace of this process has been accelerating. The time between the discovery of nuclear fission and the first atomic bomb was measured in years. The development of genetic engineering from theoretical possibility to practical application happened within decades. Artificial intelligence has progressed from science fiction to existential concern in even less time. This acceleration matters because it affects our ability to adapt to the consequences of our innovations. Biological evolution operates on timescales of thousands or millions of years. Cultural evolution can happen much faster, but still typically requires generations to fully integrate new ideas or behaviors. Technological evolution now happens so rapidly that we're forced to make decisions about the future of our species and our planet based on technologies we barely understand, with consequences we can't fully predict. The graveyard of worlds might be filled with civilizations that couldn't navigate this acceleration, species that developed dangerous capabilities faster than they developed the wisdom to use them safely. The same intelligence that allowed them to manipulate their environments eventually gave them the power to destabilize those environments beyond recovery. But there's another possibility, one that's both more hopeful and more demanding. Maybe intelligence, properly understood, includes the ability to recognize and avoid these self-destructive tendencies. Maybe true intelligence isn't just the ability to solve immediate problems, but the wisdom to anticipate long-term consequences and choose actions that preserve the conditions for continued existence. This would represent a kind of evolutionary transition, a shift from intelligence that maximizes short-term advantage to intelligence that optimizes for long-term survival. Such a transition wouldn't be automatic or inevitable. It would require conscious effort, a deliberate choice to prioritize stability over growth, sustainability over efficiency, wisdom over cleverness. The civilizations that successfully make this transition might be the hidden survivors we speculated about earlier. They would have learned to use their intelligence not to dominate their environments, but to integrate with them so seamlessly that their technological capabilities become nearly invisible. They would have solved the intelligence paradox by developing forms of intelligence that enhance, rather than threaten, the stability of their worlds. From our current perspective, such civilizations might seem almost impossibly advanced, not because of their technology, but because of their restraint. They would have learned to say no to innovations that serve short-term interests, but threaten long-term survival. They would have developed institutions capable of making decisions across timescales longer than individual lifetimes. They would have found ways to maintain the curiosity and creativity that drive technological progress, while avoiding the pitfalls that have apparently claimed so many other species. Whether we're capable of making such a transition remains an open question. Our history suggests that we're extraordinarily good at solving immediate problems and extraordinarily poor at anticipating distant consequences. We've repeatedly chosen short-term advantage over long-term sustainability, individual benefit over collective welfare, growth over stability. But we're also the first species in Earth's history to be aware of these tendencies, to recognize the patterns that have led other civilizations to failure. That awareness creates possibilities that didn't exist for previous experiments in intelligence. We can study the mistakes of the past, model the consequences of current trends, and potentially choose different paths forward. The challenge is whether we can develop the institutional and cultural mechanisms needed to act on that awareness. Whether we can create decision-making processes that account for consequences decades or centuries in the future. Whether we can find ways to coordinate action across the global scale needed to address planetary-level challenges. Whether we can learn to measure success in terms of long-term sustainability rather than short-term growth. These aren't just technical challenges. They're fundamentally about the evolution of intelligence itself, the development of new forms of thinking that can match the scale and complexity of the problems we've created. We need intelligence that can think across generations, across species, across the entire interconnected web of life that supports our existence. The Graveyard of Worlds suggests that most experiments in intelligence never develop these capabilities, that the same qualities that make technological civilization possible also make it inherently unstable. That intelligence, as it typically evolves, contains the seeds of its own destruction. But the existence of that graveyard also creates a selection pressure, a filter that eliminates forms of intelligence that can't transcend their self-destructive tendencies. If we can learn from the failures of others, if we can develop the wisdom to match our power, if we can find ways to use of long-term survival our intelligence in service rather than short-term advantage, then we might join the ranks of civilizations that learn to thrive within the bounds of their planetary systems. The choice isn't just about technology or policy or economics, though all of those matter. It's about the fundamental direction of human consciousness, whether we'll continue to see ourselves as separate from and superior to the natural world, or whether we'll learn to see ourselves as part of an interconnected system that requires our participation to remain stable. This perspective transforms how we think about intelligence itself. Instead of seeing it as the ability to manipulate and control, we might begin to see it as the ability to understand our place within larger systems and act in ways that preserve the conditions for continued existence. Instead of measuring success by how much we can change our environment, we might measure it by how well we can maintain the stability that allows consciousness to persist. Such a shift wouldn't require abandoning technology or returning to some imagined pre-industrial paradise, but it would require developing technologies that enhance rather than degrade the planetary systems we depend on. It would require economic models that account for the true costs of resource depletion and environmental damage. It would require political systems capable of making decisions that benefit future generations, even when those decisions require present sacrifices. Most fundamentally, it would require a new understanding of what intelligence is for. Not just a tool for solving problems or accumulating advantages, but a responsibility for maintaining the conditions that make intelligence possible in the first place. A way of participating in the cosmic experiment of consciousness that honors both the rarity of our situation and the delicate balances it depends on. The Graveyard of Worlds reminds us that this experiment has been tried many times before and that most attempts end in silence. But it also reminds us that each attempt is unique, that the specific combination of circumstances that gave rise to our form of intelligence has never existed before and will never exist again. We're not just another data point in a cosmic statistical analysis. We're a singular opportunity for consciousness to understand and perhaps transcend the limitations that have claimed so many others. Whether we seize that opportunity or become another cautionary tale written in geological layers depends on choices we're making right now. Not just the big policy decisions that make headlines, but the countless small choices about how we live, what we value, how we treat the world that sustains us. Every moment we continue to exist as a technological civilization capable of contemplating our own existence is another moment we've successfully navigated the challenges that ended so many other experiments in intelligence. Every generation that inherits a stable climate and functioning ecosystems is receiving a gift that most worlds in the galaxy have apparently never been able to provide. The universe doesn't guarantee that we'll continue to receive that gift, but it does provide us with the awareness needed to recognize its value and the intelligence needed to work toward preserving it. Whether we use those capabilities wisely or whether we squander them in pursuit of shorter-term goals remains the defining challenge of our time. The graveyard waits with infinite patience, neither hoping for our success nor fearing our failure. It simply exists as a reminder that every form of intelligence eventually faces the same fundamental choice. Learn to live within the bounds of planetary systems, or join the silent majority that couldn't make that transition. For now, we remain among the living, still capable of writing our own ending to this cosmic story. But the time for writing that ending grows shorter with each passing year, and the consequences of the choices we're making now will echo through geological time, long after any memory of our individual lives has faded into the deep archives of planetary history. The question is no longer whether intelligence can emerge in the universe. We are proof that it can. The question is whether it can learn to survive its own success, whether consciousness can develop the wisdom to match its power, whether the cosmic experiment in self-awareness can continue or must join the countless silent worlds that tried and couldn't quite hold on. That question remains open, and how we answer it will determine not just our future, but the future of awareness itself in this corner of space and time. The weight of that realization settles differently when you consider what it means for the countless worlds we haven't found yet. Right now, as we speak, there are telescopes scanning distant star systems, analyzing the light from planets we'll never visit, searching for the chemical signatures that might indicate life. But what if most of what we're finding isn't life as it exists today, but life as it existed millions of years ago, preserved in atmospheric compositions that no longer make sense? Think about it this way. When we detect oxygen in a planet's atmosphere, we celebrate it as a potential biosignature, evidence that photosynthetic organisms might be producing it faster than geological processes can consume it. But oxygen is a reactive gas. Without constant replenishment, it disappears from an atmosphere relatively quickly. So when we find it around a distant star, we're seeing either a world where life is actively producing it right now, or a world where life was producing it recently enough that the oxygen hasn't had time to fade away. But what about the worlds where that oxygen signature disappeared 1,000,000 years ago, or 10 million? Those planets might still be in the habitable zone, still the right size and temperature for life, but their atmospheres would have returned to the background chemistry of a lifeless world. From our perspective, they'd be indistinguishable from planets that never developed life at all. This creates a profound observational bias in our search for life beyond Earth. We're naturally drawn to the worlds that are currently active, currently producing the dramatic chemical signatures that our instruments can detect across interstellar distances. But for every world like that, there might be dozens of others that once produced those same signatures and now sit quietly in the graveyard, their stories written only in geological layers we'll never be able to read. The implications go deeper than just statistics about how common life might be. They touch on fundamental questions about the nature of planetary evolution and the role that life plays in shaping the worlds it inhabits. Because life doesn't just exist on a planet, it transforms it. Over billions of years, living organisms alter atmospheric chemistry, change the composition of oceans, modify the reflectivity of surfaces, even influence the rate at which rocks weather and erode. These transformations can create feedback loops that either stabilize or destabilize planetary systems. On Earth, life has generally acted as a stabilizing force, helping to maintain conditions within the narrow range that allows continued habitability. But there's no guarantee that this relationship always works out so favorably. Life might also trigger changes that ultimately make its homeworld uninhabitable, consuming resources faster than they can be replenished, or altering atmospheric chemistry in ways that lead to runaway climate effects. Consider what this means for our understanding of planetary habitability. We tend to think of the habitable zone as a fixed region around a star where conditions are just right for liquid water. But the real picture is far more dynamic. A planet's habitability depends not just on its distance from its star, but on the complex interplay between its geological processes, its atmospheric evolution, and the life forms it might support. A world might enter the habitable zone with perfect conditions for life to emerge and flourish. But over millions of years, that life might alter the planet in ways that gradually push it out of the habitable range. The very success of biological processes could sow the seeds of their own destruction, creating a kind of planetary-scale tragedy where life undermines the conditions that allowed it to exist in the first place. This dynamic might be one of the primary mechanisms by which worlds join the graveyard. Not through dramatic catastrophes like asteroid impacts or supernovae, but through the slow, inexorable process of life consuming the conditions that sustain it. A planet might remain technically within the habitable zone, while its biosphere gradually collapses under the weight of its own success. From our current vantage point, it's impossible to know how common this scenario might be. We're still learning to read the signs of past life in our own solar system, let alone on worlds orbiting distant stars. But the possibility suggests that the graveyard of worlds might be filled not just with planets that never developed life, but with planets where life developed too successfully for its own good. This perspective adds urgency to our own situation. We're living through a period when human activity is altering Earth's systems at a pace and scale that has no precedent in the planet's history. We're changing atmospheric chemistry, ocean pH, global temperature, and biodiversity at rates that dwarf most natural processes. In many ways, We're conducting an uncontrolled experiment in planetary-scale engineering, with our own survival as the stakes. The question isn't whether we're powerful enough to alter our planet's habitability. We've already demonstrated that capability beyond any reasonable doubt. The question is whether we're wise enough to alter it in ways that preserve, rather than undermine the conditions we depend on. Whether we can learn from the apparent failures of countless other worlds, or whether we're destined to repeat patterns that have played out across the galaxy for billions of years. The search for life beyond Earth takes on a different character when viewed through this lens. We're not just looking for confirmation that we're not alone in the universe. We're looking for examples of how the relationship between life and planetary habitability plays out under different circumstances. We're searching for case studies in success and failure, hoping to understand the factors that determine whether a living world thrives for billions of years or burns out in a few million. Each exoplanet we study, each atmospheric composition we analyze, each chemical signature we detect or fail to detect, adds another data point to our understanding of these cosmic patterns. Some worlds will teach us about the conditions that allow life to emerge. Others will show us how life can maintain planetary habitability over deep time. And some, perhaps most, will demonstrate the various ways that promising beginnings can lead to silent endings. The tragedy of the graveyard isn't just that so many worlds fail to maintain life. It's that each failure represents a lost opportunity for the universe to understand itself through conscious observation. Every civilization that collapsed before reaching technological maturity, every biosphere that died before evolving intelligence, every planet that lost its habitability before life could spread beyond its surface represents a path not taken, a story that will never be told. This makes the continuation of consciousness, wherever it exists, not just a local concern, but a cosmic responsibility. If intelligence is indeed rare in the universe, if most experiments in self-awareness end in the silence of the graveyard, then every moment of continued consciousness becomes precious beyond measure. Not because we're special or chosen, but because we might be among the few places where the universe is currently capable of contemplating its own existence. That possibility transforms how we think about the choices we're making right now. They're not just decisions about human welfare or economic systems or political arrangements. They're decisions about whether consciousness continues to exist in this part of space and time, whether the cosmic experiment in self-awareness proceeds or joins the countless silent worlds that tried and couldn't maintain the delicate balance required for continued existence. The universe offers no guidance about which choice we should make. It records outcomes with equal indifference, preserving the signatures of both success and failure in the slow accumulation of geological time. But for us, caught in the middle of this vast experiment, the stakes couldn't be higher. We're deciding not just our own fate, but the fate of awareness itself in our corner of the cosmos. And perhaps that's the most sobering realization of all. That consciousness, this remarkable property that allows matter to reflect on its own existence, might be far more fragile than we ever imagined. That the graveyard of worlds isn't just a collection of failed planets, but a vast archive of interrupted conversations, experiments in awareness that began with such promise and ended in such silence. Yet here we are, still talking, still wondering, still capable of recognizing both our extraordinary position and our extraordinary vulnerability, still able to choose whether we'll add our voice to the chorus of consciousness that somehow persists in this seemingly indifferent universe, or whether we'll become another entry in the archive of worlds that almost made it but couldn't quite hold on. The graveyard waits, patient as always, neither hoping for our success nor mourning our potential failure. It simply exists as a reminder that every moment of awareness is borrowed time, every generation of consciousness a temporary victory against the universe's tendency towards silence and simplicity. How long we can sustain that victory remains the most important question we've ever faced. And the answer depends on choices we're making right now, in this brief window when our world still breathes and our future remains unwritten. The silence between stars isn't empty waiting. It's full of stories we're only beginning to suspect exist. When we consider the possibility that Earth sits surrounded by worlds that once thrived and now lie quiet, we're forced to reckon with something that challenges our most basic assumptions about progress, about permanence, about what it means to succeed in a universe that operates on scales we can barely comprehend. The conventional wisdom suggests that if life emerges somewhere, it should tend toward greater complexity over time. Simple organisms evolving into more sophisticated ones, ecosystems becoming richer and more diverse, intelligence eventually arising to contemplate its own existence and reach toward the stars. It's a narrative of inevitable advancement, a story that culminates in civilizations capable of spreading across galaxies and ensuring their own permanence. But what if that narrative is fundamentally wrong? What if the universe's default trajectory isn't toward greater complexity and expansion, but toward equilibrium and restraint? What if the civilizations that survive are precisely those that learn to live quietly, to maintain themselves within the bounds of their planetary resources, to resist the urge to grow beyond the carrying capacity of their worlds? This possibility forces us to reconsider what success actually looks like on cosmic scales. The civilizations we're most likely to detect from Earth are those that burn brightest, consume the most energy, make the most dramatic alterations to their environments. They're the ones sending powerful signals across interstellar space, the ones whose industrial activity creates obvious atmospheric signatures, the ones whose cities might be visible from light years away. But these highly visible civilizations might also be the ones most likely to exhaust their resources, destabilize their climates, or trigger the kinds of cascading failures that push worlds beyond the point of recovery. Their visibility might be a symptom of unsustainable practices rather than a sign of long-term success. They might be burning bright precisely because they're burning out. The truly successful civilizations might be the ones we can't see. Species that learned to harness energy so efficiently that they produce minimal waste heat. Societies that developed manufacturing processes so clean they leave no atmospheric signatures. Cultures that integrated their cities so seamlessly with natural ecosystems that they're invisible from space. Civilizations that achieve genuine sustainability by learning to mimic the elegant efficiency of natural systems. Such societies would be extraordinarily difficult to detect using our current methods. They might communicate using technologies we haven't discovered, power their civilizations with energy sources that produce no obvious byproducts, manage their populations and resources so carefully that their worlds appear entirely natural from the outside. They would have solved the fundamental challenge that faces every technological species: how to maintain complexity without consuming the foundations that support it. The search for these hidden civilizations would require entirely different approaches. Instead of looking for the obvious signatures of high-energy technology, we'd need to search for signs of intelligence that has learned to work within natural limits. We'd look for planets that are too stable, too well-balanced, too perfectly managed to be entirely the product of unconscious processes. The challenge would be enormous. Natural planetary systems can achieve remarkable stability through purely physical and biological mechanisms. Distinguishing between a world that's naturally well-balanced and one that's being carefully tended by an invisible civilization would require understanding planetary evolution with extraordinary precision. We'd need to know exactly what a planet should look like based on its age, composition, stellar environment, and orbital characteristics. Then we'd search for subtle deviations from that expected state, patterns that might indicate intelligent management disguised as natural processes, a climate system that's slightly too stable for the planet's position in its star's evolution, an atmospheric composition that's perfectly balanced in ways that seem improbable without active maintenance, ecosystems that show signs of careful cultivation hidden within apparently wild landscapes. Even then, the most successful civilizations might be those that have learned to guide their world so skillfully that their intervention is genuinely undetectable. They might work with natural processes rather than against them, nudging planetary systems towards stability in ways that appear entirely organic. Their greatest achievement wouldn't be the conquest of nature, but perfect partnership with it. This vision of mature civilization challenges many of our assumptions about progress and achievement. We tend to measure success by growth, by expansion, by the accumulation of power and resources, but a civilization capable of maintaining itself indefinitely on a single world might represent a higher form of achievement than one that spreads across multiple star systems, but ultimately exhausts the resources of each. The mathematics of exponential growth make this almost inevitable. Any civilization that prioritizes expansion over sustainability will eventually encounter limits, whether those limits are imposed by the carrying capacity of their homeworld, the energy requirements of interstellar travel, or the simple fact that resources are finite everywhere. The outcome is the same. Growth-oriented civilizations either learn to change their approach, or they collapse under the weight of their own success. The civilizations that survive might be those that recognized these limits early and chose to optimize for longevity rather than expansion. They might have developed technologies that enhance quality of life without increasing resource consumption. They might have found ways to satisfy human curiosity and creativity within the bounds of what their worlds could sustainably support. They might have discovered that the universe is rich enough in complexity and beauty that a single planet can provide infinite opportunities for exploration and growth. Such civilizations would face their own challenges. Maintaining technological capability without the stimulus of resource pressure might require entirely new approaches to innovation and social organization. Preventing stagnation while avoiding unsustainable growth might demand forms of wisdom that no civilization has yet achieved. Finding meaning and purpose within limits might be harder than the endless frontier expansion that has driven human development for millennia. But the rewards would be proportional to the challenges. A civilization that achieved true sustainability wouldn't just survive for thousands or millions of years, it might persist for billions. Watching its star evolve through its entire lifetime, adapting gradually to changing conditions while maintaining the essential characteristics that define its identity. It might become a permanent feature of its planetary system, as stable and enduring as the geological processes that shape its world. From our current perspective, such longevity seems almost impossible to imagine. Human civilization is measured in thousands of years, individual lives in decades. The idea of maintaining technological society across billions of years requires thinking on scales that stretch our conceptual abilities to their limits. Yet the physics of stellar evolution and planetary dynamics operate on exactly those scales. A civilization that learns to match its development to those natural rhythms might find forms of permanence that are genuinely cosmic in scope. The question becomes whether we're capable of making such a transition. Our entire history as a species has been defined by expansion, by the conquest of new territories and the exploitation of new resources. We've solved every resource limitation by finding new sources of supply, every environmental challenge by developing new technologies, every population pressure by expanding into new areas. But we've reached the point where further expansion within our current paradigm becomes self-defeating. We're altering our planet's climate faster than we can adapt to the changes. We're consuming resources at rates that can't be maintained indefinitely. We're creating waste products that accumulate faster than natural processes can absorb them. The approaches that brought us to this point might not be sufficient to carry us beyond it. The transition to genuine sustainability would require changes that go far deeper than technology or policy. It would require reimagining our relationship with the natural world, reconsidering our definitions of progress and success, rediscovering forms of meaning and purpose that don't depend on endless growth and expansion. This isn't a call for primitivism or the abandonment of technology. The hidden civilizations we're imagining would likely possess technologies far more sophisticated than ours, just applied in ways that enhance rather than degrade the planetary systems they depend on. They might have mastered fusion power, molecular manufacturing, genetic engineering, artificial intelligence, and countless other capabilities we're still developing. The difference would lie not in what they can do, but in what they choose not to do. Such restraint might represent the highest expression of intelligence. Not the ability to consume and expand without limit, but the wisdom to recognize limits and find fulfillment within them. Not the power to remake the world according to our desires, but the understanding to see ourselves as part of systems larger and more complex than any individual species or civilization. The graveyard of worlds might be filled with civilizations that possessed tremendous technological capabilities, but lacked this deeper wisdom. Species that could split atoms and splice genes and travel between planets, but couldn't learn to live sustainably on the worlds that gave them birth. Their failures might not reflect limitations in their science or engineering, but gaps in their understanding of what intelligence is ultimately for. From this perspective, our current moment becomes even more crucial. We're approaching the point where our technological capabilities will either enable genuine sustainability or trigger the kinds of cascading failures that have claimed so many other worlds. We have the knowledge needed to understand our impact on planetary systems and the tools needed to modify that impact in more sustainable directions. What we don't yet have is the collective wisdom to consistently choose long-term stability over short-term advantage. We haven't developed the institutional mechanisms needed to make decisions across the timescales on which planetary systems operate. We haven't learned to measure success in ways that account for the full costs of our activities, including their impacts on the systems that sustain us. These challenges aren't primarily technical. They're fundamentally about the evolution of intelligence itself, the development of forms of thinking and decision-making that can match the complexity and scale of the problems we've created. We need intelligence that can see beyond individual lifespans, beyond national boundaries, beyond the narrow interests of our own species. We need wisdom that can recognize the interconnections between human welfare and planetary health, between short-term prosperity and long-term survival. The hidden civilizations, if they exist, would have developed these capabilities. They would have learned to think and act as planetary citizens, as conscious participants in the cosmic experiment of habitability. They would have found ways to satisfy their needs and desires without undermining the conditions that make consciousness possible in the first place. Whether we can join their ranks remains the defining question of our time. Whether we can develop the wisdom to match our power, the restraint to balance our ambitions, the foresight to choose paths that preserve rather than consume the foundations of our existence. Whether we can learn to live as permanent residents of Earth rather than temporary exploiters of its resources. The universe offers no shortcuts to this wisdom, no technological fixes that can substitute for the hard work of learning to live within planetary boundaries. But it does provide examples, both positive and negative, of how the experiment in intelligence can unfold. The graveyard reminds us of the costs of failure. The hidden civilizations, if we can learn to detect them, might show us what success actually looks like. For now, we remain in the middle of the story, still capable of writing our own ending, still able to choose whether we'll join the silent worlds or discover what lies beyond the horizon of sustainable civilization, still participants in the cosmic experiment of consciousness with the responsibility that participation entails and the opportunities it creates. The choice, as always, remains ours to make. But the time for making it grows shorter with each passing year. and the consequences will echo through geological time, long after any memory of our individual struggles has faded into the deep archives of planetary history. The weight of these realizations settles into something even more profound when we consider what it means to be conscious during what might be a pivotal moment in our planet's story. Right now, as you're listening to these words, Earth continues its ancient dance around the sun, its systems operating according to rhythms that have persisted for billions of years. The oxygen you're breathing was produced by countless generations of photosynthetic organisms. The ground beneath you is composed of materials that have been recycled through geological processes older than complex life itself. Yet within this deep continuity lies something unprecedented. For the first time in Earth's history, a species has emerged that can perceive these vast scales of time and space. We can look backward through the geological record and see the traces of previous worlds. We can look outward to distant stars and imagine the stories of planets we'll never visit. We can look forward and model the potential consequences of our current choices. This perspective brings with it a peculiar form of responsibility. Previous mass extinctions happened to life on Earth, driven by forces beyond the control of any individual species. Asteroid impacts, volcanic eruptions, climate shifts caused by orbital variations or stellar changes. But we're living through what might be the first extinction event caused by life becoming aware of its own impact, and continuing anyway. The paradox is striking. The same intelligence that allows us to understand our fragility also gives us the power to either protect or destroy the conditions that created us. We can model climate systems with extraordinary precision, yet we continue to alter them faster than our models can predict their responses. We can trace the connections between industrial activity and atmospheric chemistry, yet we struggle to coordinate the global action needed to address those connections. This suggests that intelligence, at least as it typically evolves, might contain within it the seeds of its own limitations. The qualities that make technological civilization possible, curiosity, ambition, the drive to solve immediate problems, might also make it inherently unstable over the long term. A species smart enough to alter planetary systems might not automatically be wise enough to do so responsibly. The graveyard of worlds might be filled with civilizations that faced exactly this challenge and couldn't resolve it. Not because they lacked scientific knowledge or technological capability, but because they couldn't develop the collective wisdom needed to manage their own power. They might have understood perfectly well what they were doing to their worlds, but found themselves unable to change course quickly enough to avoid the consequences. From this perspective, our current situation becomes less about discovering new technologies and more about evolving new forms of consciousness. We need ways of thinking that can operate across the timescales on which planetary systems function. We need decision-making processes that can account for consequences that might not manifest for generations. We need economic systems that recognize the true costs of environmental degradation and resource depletion. Most fundamentally, we need to develop what we might call planetary consciousness. The ability to see ourselves not as separate from the natural world, but as conscious participants in the same systems that regulate our planet's habitability. To understand that human welfare and planetary health are not competing interests, but different aspects of the same fundamental challenge. This kind of consciousness doesn't emerge automatically. It requires deliberate cultivation, the same way that scientific thinking or artistic sensibility must be developed through practice and education. We need to learn to feel the connections between our daily choices and their global consequences, to viscerally understand that the stability we depend on is neither guaranteed nor independent of our actions. The difficulty lies in the mismatch between human psychology and planetary timescales. We're evolved to respond to immediate threats and opportunities, to focus on the needs of our families and communities, to think in terms of seasons and lifespans rather than geological epochs. The threats we now face operate on scales that don't trigger our instinctive responses, even when we understand them intellectually. Yet this same mismatch might explain why consciousness evolved in the first place. Perhaps intelligence emerges precisely when species reach the point where their immediate survival strategies begin to threaten their long-term viability. When the short-term thinking that served them well during earlier stages of evolution becomes inadequate for the challenges they've created for themselves. If this is true, then consciousness might represent not just an accident of evolution, but a necessary response to the complexity that intelligence generates. A way for matter to develop the foresight needed to navigate the increasingly sophisticated challenges that emerge when simple organisms become capable of altering their environments. The question becomes whether consciousness can evolve quickly enough to address the problems that intelligence creates. Whether we can develop planetary awareness before our technological capabilities overwhelm the systems that sustain us. Whether the same processes that gave rise to consciousness in the first place can be accelerated to meet the urgent timeline we're now facing. The answer might depend on recognizing that consciousness itself is still evolving. That the forms of awareness we've developed so far, focused primarily on individual survival and social cooperation, represent only early stages in a process that could potentially continue. That we might be capable of developing new forms of consciousness specifically adapted to the challenges of planetary stewardship. Such evolution wouldn't happen automatically. It would require conscious intention, the deliberate cultivation of ways of thinking and perceiving that don't come naturally to minds shaped by millions of years of more immediate concerns. We'd need to learn to feel the pulse of atmospheric chemistry, to sense the health of ocean currents, to perceive the slow breathing of geological processes that maintain our world's stability. This expanded consciousness wouldn't replace our more familiar forms of awareness. We'd still need to care for our families, pursue our individual goals, respond to immediate challenges and opportunities. But we'd also need to develop the ability to hold these personal concerns within the larger context of planetary systems, to see how our individual choices connect to the great cycles that sustain all life. The hidden civilizations we've imagined might have achieved exactly this kind of expanded consciousness. They might have learned to think as planetary citizens, to feel themselves as conscious expressions of their world's ongoing evolution. Their technologies might be extensions of this consciousness, tools for participating in planetary processes rather than dominating them. Such civilizations wouldn't see themselves as separate from their environments, but as conscious aspects of planetary systems that had evolved the capacity for self-reflection. Their greatest achievement wouldn't be the conquest of nature, but the integration of intelligence with the natural processes that created it. They would have solved the intelligence paradox by developing forms of consciousness that enhance rather than threaten planetary stability. Whether we're capable of such a transformation remains the central question of our time. Whether we can learn to think and feel and act as conscious participants in Earth's ongoing story, rather than as temporary exploiters of its resources. Whether we can develop the expanded awareness needed to navigate the challenges we've created, or whether we'll remain trapped within forms of consciousness that are inadequate to the scale of our impact. The universe provides no guarantee that such evolution is possible. Consciousness might be inherently limited by the evolutionary pressures that created it, unable to transcend the short-term thinking that served our ancestors well but threatens our descendants. The graveyard of worlds might be filled with species that reached the same crossroads we're now facing and couldn't make the transition to planetary awareness. But the universe also provides no evidence that such evolution is impossible. We're the first species we know of to even recognize the need for this kind of transformation. The fact that we can imagine planetary consciousness, that we can see the connections between individual choices and global consequences, might itself be evidence that such consciousness can emerge. The development of this expanded awareness wouldn't be a luxury or an abstract philosophical goal. It might be the most practical necessity we face, the foundation upon which all our other efforts to address planetary challenges must rest. Without the ability to think and feel ourselves as part of larger systems, our technical solutions will remain fragmentary, our policy responses inadequate to the scope of the problems we're trying to solve. The cultivation of planetary consciousness would require changes in education, in media, in the stories we tell ourselves about who we are and what our purpose might be. It would require learning to see beauty and meaning in stability rather than just in growth, in balance rather than just in achievement, in the subtle harmonies that maintain life rather than just in the dramatic disruptions that command attention. Most of all, it would require patience with forms of change that operate on timescales longer than individual lifespans or political cycles. The development of genuine sustainability might take generations, requiring forms of coordination and commitment that extend far beyond any individual's ability to control or even witness their completion. Yet this long-term perspective might also be liberating. Instead of seeing ourselves as responsible for solving every challenge within our own lifetimes, we might begin to see ourselves as contributors to a much larger project, participants in the gradual evolution of consciousness toward forms capable of maintaining planetary stability. Each generation would add its own contributions to this ongoing transformation. Some might develop new technologies that work with, rather than against, natural systems. Others might create institutions capable of making decisions across longer timescales. Still others might cultivate the forms of consciousness that make such technologies and institutions possible in the first place. The Graveyard of Worlds reminds us that this project is not guaranteed to succeed. Many other experiments in consciousness have apparently failed to make the transition from individual awareness to planetary wisdom. But it also reminds us that each attempt is unique, that the specific circumstances that gave rise to our form of consciousness have never existed before and will never exist again. So here we are, at the edge of a question that has no easy answers, only deeper mysteries. We've walked together through the possibility that Earth isn't the rare success story we like to imagine, but perhaps just the latest in a long line of attempts at creating a world where life can flourish. We've considered the graveyard of worlds that might surround us, silent witnesses to experiments that began with such promise and ended in such quiet. If you've stayed with me through this long contemplation, thank you. Questions like these don't offer the satisfaction of clear conclusions, but they do something perhaps more valuable. They change how we see the ground beneath our feet, the air we breathe, the delicate balance that keeps our world spinning in that narrow band where life can persist. Whether Earth will remain among the living worlds or eventually join that vast collection of silent planets scattered across the galaxy depends on choices we're making right now. The universe watches with patient indifference, but for us, caught in the middle of this cosmic experiment, every moment of continued consciousness is both a gift and a responsibility. Sweet dreams, fellow travelers through deep time.